Welcome back. All right, so what I want to do in this video is continue on with a little more of Lineweaver-Burk plots. Okay, this is going to be a more rigorous video. It's going to involve a little bit, just a teeny bit of calculus. We're going to take a derivative and then analyze it. And we're going to talk about the kinetic interpretation of ultimately what it means to approach the maximum rate of the enzyme, or the Vmax. Okay, so my name is Kevin Tokoph. Make sure to like this video and subscribe to the channel. All right, so this is that graph that I generated for a Michaelis-Menten enzyme. So that equation that we use, which is the Michaelis-Menten equation, is that the rate is equal to the Vmax of the enzyme times the substrate concentration divided by the sum of Km plus S. All right, so this is the Michaelis-Menten equation that we ultimately derived in one of the previous videos. And if you notice about this plot up here, notice that the y-axis is the rate, the x-axis is the substrate concentration, and my question to you is, if I have this hyperbolic curve, okay, we mentioned again in actually two other videos that this line that represents what V value or rate value is the Vmax, this is a horizontal asymptote, okay? And the nice thing about this curve right here is you may look at it and say, well, maybe it diverges, maybe it goes off to an infinite rate. But it turns out that the nice thing is it actually converges to some value. And that value is this asymptote, or the Vmax. Now my question to you is, how would you mathematically figure out from this plot, not the Lineweaver-Burk plot, how would you use this graph to figure out what the Vmax was? Well, if you think about this, notice what's happening. What's the slope of this line right there? So the slope is like that right there. And notice as I increase the substrate concentration, what's happening to the slope? The slope is getting shallower and shallower, right? And so you can imagine that as you go out to a substrate concentration, keep going to the right on this, what's going to be the slope out here? The slope should be zero, should be flat. And theoretically, when the Vmax is reached, if it gets closer and closer and closer to the asymptote, the slope should be zero. So we're going to use that identity, that the Vmax is where the change in rate with respect to substrate concentration is zero. So let's actually figure out what that derivative is, because that's what this is. dV ds is a derivative. So what we're going to do is we're going to differentiate this Michaelis-Menten equation. Well, how do you do that? Well, we're differentiating with respect to s, and we have an s in the numerator and denominator. So my guess as to which technique to use would have to be quotient rule. So what I'm going to do is I'm going to take the denominator, Km plus s, and multiply times the derivative of the numerator. And since this is s to the first power, if I differentiate that, it just becomes Vmax. And then I'm going to subtract off the numerator, Vmax times s, times the derivative of the numerator. Km is a constant, so this derivative is 0, plus the derivative of s to the first power is just 1. So it's just minus Vmax s. And then that's divided by the square of the denominator. So that's, if you actually square this, it actually becomes Km squared plus 2Kms plus s squared. Okay? And that equals 0, right? Because this derivative has to equal 0. Well, what I'm going to do is I'm going to clean it up a little bit. I notice that I'm going to factor out the Vmax. So Vmax is two terms here, so I'm going to factor that out. And I get that's all multiplied by Km plus s minus s. If you think about this, it's plus s minus s, so that actually, those two cancel to 0. And ultimately what you're left with 0 is equal to Vmax times the Km divided by Km squared plus 2Kms plus s squared. And it turns out that in terms of simplifying this derivative, that's pretty much all you can do. And you can play around with this, but you really won't be able to simplify it anymore. So how do I prove that this is equal to 0? Well, I should think about just logically, if I have, since I'm dealing with s as the independent variable, is there any s in the numerator, any substrate? No. There's only s in the denominator, right? I notice have an s to the first term and an s to the second term here. So what would s technically have to be for this to be 0? Well, if you think about it, what is any, like Vmax and Km, those are just numbers. What's any number, what do you have to divide any number by to get 0? You have to divide by infinity, right? So actually this rigorous definition mathematically, not chemically of course, but mathematically, is that the derivative of the rate with respect to the substrate concentration is 0 only when the the substrate concentration is infinity. So if you plug infinity in for S's here, I don't care what Km and Vmax are, it's 0. All right? But there's a problem with this, and the obvious problem is, how do you have a concentration of anything that's infinity, right? Because remember, concentration is usually in something like moles per liter. Well, how do you have an infinite number of moles of anything, particularly in something as small as a cell? Or if you're doing it in a lab, in a test tube, I mean, how do you have an infinite concentration? The answer is you can't, obviously. And then on top of that, another consideration is even if you could have an infinite number of molecules, how do you concentrate them to have a concentration of infinity? You can't. There's even limits to solubility in any solvent. So this statement is really impossible. Not mathematically. Mathematically, it's true. But the problem is that we're dealing with enzymes, and they operate by a little bit of a different principle than just straight math. But it turns out that they do have a Vmax when S is not infinity. How does that work? What is the kinetic interpretation of this? Well, the interpretation is that this limit is technically when the substrate concentration is a finite number, but that number is when the substrate concentration is saturating. So what does that mean? Well, I'm going to use two examples, one abstract and then one that's more to do with enzymes. So let's say I have an enzyme. Say I have an enzyme, all right? And let's say the rate of this enzyme is it can catalyze 10 reactions, or it can get rid of 10 molecules per second, right? So 10 molecules per second, right? So if I give this in 1 second, if I give it 2 molecules, has it hit its Vmax? No, because its Vmax is 10 molecules per second. If I give it 4 molecules in that 1 second, it's not at its Vmax. If I give it 9 molecules in that second, is it at its Vmax? No, but if I give it 10 molecules in that second, it's operating at its maximum rate. Now the question is, what happens if I give it 20 molecules in that second? Well, it's still only going to catalyze 10 per second. Let's see, what did I do? All right, it's still only going to catalyze 10 molecules per second. Even if I put 20 in its vicinity in that second, it's only able to catalyze 10. So what we would say is if we wanted to experimentally determine its maximum rate, we should put a lot more than 10 molecules per second in there, right? We should put 20, maybe even 1,000, right, to ensure that it's at its maximum rate. So when we say a substrate concentration is saturating, we have to look at the number of molecules that the enzyme can catalyze per second and just put a lot more than that. Because because of the rate, because there is a maximum to it, there's a finite number of molecules that can be reacted per second or per minute, depending. Okay? And if you give any more than that, that's considered saturating. You don't have to have an infinite number. So a more realistic number, and this is actually pretty crazy, there's an enzyme called catalase. Catalase is an enzyme that detoxifies hydrogen peroxide. Hydrogen peroxide is just a molecule like this. Anyone want to take a guess how many reactions catalase can do per second? It's actually an unfathomable number. Catalase can catalyze 40 million hydrogen peroxides per second. Now, I don't know about you, but whenever I'm trying to get people to have a little bit of an appreciation for how fast enzymes are, this is what I use. And certainly this is the fastest enzyme in nature, but certainly 40 million hydrogen peroxides per second that it's catalyzing is unfathomable. So suppose I wanted to give a saturating amount of HOOH, or H2O2, for catalase. Would I give 20 million? No, 20 million is beneath the turnover number. That's what we call this. We'll talk more about that in a future video. But this can turn over, it can catalyze 40 million per second, so if I give it 20 million, that's less than it. It's not saturating. If I give it 100 million, so maybe instead of 40 million, I give it 100 million, it's still only going to catalyze 40 million per second. There's just excess here, and we would consider this number saturated. So the key is you want the substrate concentration to be saturating, meaning that there's no way the enzyme can deal with any more substrate. Okay? Another way of thinking about this that you may have more of an understanding is suppose you have an hour to get a certain amount of work done. You got way behind, which I don't recommend that you do. I've done it before, it's not fun. Let's say you get way behind, right? And let's suppose you know for fact, in that hour, you could get 4 of your assignments done. Okay, maybe they're short assignments. You can get 4 assignments done. That's the max in that hour. You can get 4 assignments done. What if you have 10 assignments? Well, then theoretically, there's going to be 6 in that hour that don't get done because you can only do 4. So 4 is the maximum amount of assignments that you can do. And there's 10 assignments. You're saturated with assignments. If you only have an hour, you're saturated because you have more assignments than you can actually finish in that hour. It's kind of a grim example. Don't get that far behind, but that's the truth. So this is it's kind of a way of thinking about it in real life, sort of. But from an enzyme's perspective, if it can catalyze 40 million per second, if you give it 100 million, that concentration is also saturating. Okay. So hopefully that makes a little bit of sense, but that's the kinetic interpretation. The substrate concentration doesn't have to go to infinity to yield the maximum rate. Okay, it doesn't have to, but the substrate concentration needs to be saturating. So when you do an enzyme assay in the lab to determine its maximum rate, you really need to know what that saturating substrate concentration is. And if you know what that concentration is and you can determine it, you just add a lot more than that to make sure that it's saturated. And if it continues to be saturated for a few seconds, then it'll be at its maximum rate for a few seconds until it catalyzes enough of those substrates that the amount of it goes below the saturating amount. Okay? So this is just some other theory behind ultimately why we can't actually measure the substrate concentration at infinity, and we don't want to. And in fact, it's not infinity that's going to yield the Vmax. And actually what this is going to lead us into, talking about Lineweaver-Burke plots. And we're actually going to cover that in the next video. So join us for the Lineweaver-Burke plots. My name is Kevin Tokoph. Make sure to like the video and subscribe to the channel for future videos and notifications. Thank you. Thanks for watching.